Hello everyone. This is our first video on the predicate derivation inference rules. It will only cover universal elimination. Next videos will address existential introduction, universal introduction, and existential elimination. Two quick comments. If you haven't already watched it, I recommend watching the video on generalizations and instances because that's a basic concept that will be used in all of these videos. Also, it may look like these rules are listed in some kind of strange order, but I can tell you now that they're listed in order of ease. So we're starting with the easiest rule to apply, universal elimination, and then moving to the most challenging to apply, which is existential elimination. To see the inference rules in the book, open your textbook's front cover. That's where you see the sentential derivation rules, SD and SD+. And if you turn that page facing the front cover, on the back of that page, you'll see the derivation rules for predicate derivations. And the four rules listed on the screen are the four PD rules. Then there's a fifth rule, quantifier negation. That's considered the PD plus rule. Okay, so let's get started with universal elimination. Universal elimination, if you look at the way the rule is stated in the book, we see similar to all of our SD rules, we see a scope line. At the top of the scope line is a expression that looks a little bit like this for all xp. And then at the bottom is our rule output. We see that P followed by a set of brackets containing A/X. And this is the textbook's fancy way of expressing that the input for the inference rule is a universal generalization. Its main operator is the universal quantifier. The variable of quantification doesn't matter. It could be W, X, Y, or Z. And then the idea here is that this P stands for the open formula or the quantified expression. It is understood that that expression contains the variable of quantification. In the rule output, what we see here is, again, that expression P, and inside the brackets, this is what we're supposed to understand, that all occurrences of the variable X have been replaced by some name. In this case, A. In terms of the notation I introduced in the other video for generalizations and instances, this notation I actually prefer, we would maybe state the rule like this. So we begin, our input has an operator, universal quantifier, with some variable of quantification. I'm going to use the letter V to stand for all of our variables, W, X, Y, and Z. And then the rule output will be the result of dropping that quantifier and uniformly substituting some name N for V in all occurrences. Okay? So this is the notation that I introduced. I think it makes a lot more sense. But either way, we just have to understand what syntactically is happening. We have a universal generalization, which is our rule input. And then as our rule output, we drop the quantifier, and if necessary, with it, the outer parentheses. And we do a uniform substitution of a particular name for all occurrences of the variable of quantification. Okay? And we call that universal elimination. And we call that universal elimination too. Okay? That's the rule statement. What we want to do is see how it works. So let me give you a couple of simple illustrations of universal elimination. So suppose that we're going to start a derivation with the following. So we'll say we're going to derive some sentence, let's keep it simple, tilde B A, right? And we will then need some primary assumptions. Let's say that our first assumption is a universal y. If by, then ry. Okay, and that we are going to make a primary assumption. And then our second primary assumption will be tilde r a. Okay, so let me give us a scope line to work with here. And annotate that that is an assumption and draw our line under our primary assumption. Okay, so does that all look familiar? We have a list of numbered statements. The first is the universal generalization. All b's are r's for all y. If y is b, then y is r. And then the second one is the negation, tilde r a. Okay, and our objective is to derive the statement, the target statement, tilde ba. How should we do it? And of course, this is always the case, there are multiple ways to do it. The first step we need to take, however, is to instantiate this universal generalization. Instantiate. That means to make an instance. So what we're going to do is we're going to apply universal elimination to line 1. We'll drop the quantifier with at the outer parens, and we're going to do a uniform substitution. B A horseshoe R A. Okay? And we can instantiate to any name we like. We can drop these y's in line 1 and replace them both with any name. We could replace it with a B or a C or a D or an F. But we should instantiate to the letter A, to the name A, because that's the name that appears on the second line. And when we do that, you might already have noticed, some of you, that we now have input for the rule modus tollens. So we have a conditional line on line 3, BA horseshoe RA, and then we have the denial of the consequent on line 2. And that licenses us to write down the denial of the antecedent. And we annotate it by appealing to lines 2 and 3, modus tollens. And that's the proof. Like I said, there are other ways to do this proof, but that one is actually the shortest one. It does require that you're familiar with modus tollens. So that's our first example. I want to work through one more example. It's just about as simple as the first one. Let's take a look at what it looks like. So in this example, we're going to derive the sentence S H H. It spells sh. And here are our assumptions. For all y, for all z, if L, Y, Z, then S, Y, Z. And that's going to be a primary assumption. There's one more assumption, and that assumption is L, H, H. Okay, let me insert our scope line here. Something like that, and so that we can get started. Obviously, your eyes are probably looking at line 1 there. You got a universal generalization. It's actually a universal generalization of a universal generalization of a conditional. So what we're going to do is we're going to want to do a universal elimination on it. Universal elimination always works on the universal quantifier that is the main, has the largest scope. It is the largest, it is the main, it'll have to be the main logical operator in the sentence. We look up here on line 1, that would be the quantifier with the y variable for all y. So our instance of that generalization would start with the quantifier for all z. And so what we're going to do is we're going to take all those y's out and replace them with some name. We have full freedom what names we want to replace in place of the y. But strategically, we want to put an h there. We want to put an h there so that our result is going to end up talking to or interacting with the only other sentence we have to work with, which is on line 2. So we'll drop the y quantifier and replace those y's with h's. And the result is for all z, if LHZ, then SHZ. And that is universal elimination on line 1. We still have a universal quantifier to work with. We need to eliminate it. We need to drop it. We need to instantiate this generalization, make an instance. And so we're going to drop that quantifier, and with it the outer parentheses. The result will be LHZ horseshoe SHZ. We have to replace those variables with a name. And once again, strategically, the best name to replace there is an H. So this is line 3, universal elimination. Well, we're almost there. We're almost to our target sentence, SHH. If we look at lines 2 and 4, we have LHH on line 2. We have if LHH, then SHH. This is input for a rule, hopefully you remember, called conditional elimination. SHH is the consequent of the conditional. We get to write that down because we have the antecedent of the conditional on another line, line 2. So we would annotate that by saying 2 and 4, conditional elimination. So that is the inference rule, universal elimination, and that's how we could apply it in a couple of relatively simple proofs. And we will certainly build on this by introducing the next 3 PD inference rules in subsequent videos.